welcome to another module in this massive open online course on Bayesian minimum mean squared error estimation for wireless networks. So, yesterday we motivated, or in the previous module we basically motivated the need for estimation of a parameter h, more specifically a Bayesian parameter h. By Bayesian we mean a parameter about which there is some prior information that is available in terms of the probability density function P of h, correct. This is the prior probability density function. This is the prior probability density function. Also, we have a set of measurements or observations, which we also call the observation vector. We have a set of n observations. We can represent them using the vector y1, y2 up to yn. This is y bar, which is, we also said this is our observation, this is our observation vector, all right. And we also have the conditional probability density of the observation vector p y bar given the parameter h. Remember, we also termed this h, this quantity h is also termed as a parameter which has to be estimated, all right. So, this parameter h has to be estimated given the observations y1, y2, yn, the n observations, or the observation vector y bar, all right. And now, let us denote this estimate of h by h hat, all right. So, h hat, which is the estimate of h, is naturally going to be a function of the observation vector, all right. So, h hat, and this is the standard notation used to denote the estimate, h hat is a function of the observation vector. So, h hat is the estimate of the parameter h, and observe that, and it is important to realize that although it is a simple point, h hat is a function of the observation vector . This is a function of the observation vector y bar. Okay. And another important point to realize, although it is also a very simple point, is that the estimate h hat can only be a function of the observation vector y bar and not a function of the unknown parameter h, because h, the underlying parameter itself, is unknown, and that is the reason we are trying to estimate h. Therefore, h hat cannot depend on the unknown parameter h, and that is an important aspect. Although simple, it is an important property that has to be kept in mind. So, h hat cannot depend on h. So, it does not depend on h, or rather cannot depend on h, which is basically your unknown parameters, because h is the unknown parameter. This is the unknown, because h is the unknown parameter. Okay. Now, what we would like to do is we would like to come up with an estimate which minimizes the estimation error. Now, what is the estimation error? Estimation error is naturally the difference between the estimate and the parameter, all right. So, we have the error, this is the estimate, correct. So, this is, I have my estimate h hat of y bar minus h, this is the estimation error. Okay. And what I am going to do is I am going to consider the square of the estimation error, because I can have a scenario in which the estimation error is positive and negative and cancel each other, all right. So, I am interested in minimizing the absolute value of the error. Also, I am going to considering the square of the estimation error, and more importantly I am not interested in minimizing a particular instantiation of the estimation error, rather I am interested in minimizing the estimation error on an average sense. That is, if I repeat this experiment several times, I would like to come up with an estimator which minimizes the average estimation error. Alright, that is also termed as the mean squared error of estimation. Right. So, I am going to denote this average by the expectation operator, which gives me the basically the mean. All right. So, basically this mean also represents, this quantity also represents basically your averaging, this also represents the average, and therefore, now this total quantity that you have over here, this is known as the MSE, which is the mean squared error, and this is an important quantity that we will be considering in the rest of this course. That is the, this is the MSE or the mean squared error, and that is from which we get the term MMSE. That is, we want to find the minimum of this MSE, that is the minimum of this mean squared error. All right. Now, how do we come up with an estimator that yields the minimum of this mean squared error? All right. That is the procedure which we are going to describe. That is the general principle to obtain the minimum mean squared error estimate. That is the procedure which we are going to describe now. All right. So, now let P y bar comma h, all right, let this quantity denote the joint distribution of the observation vector y bar and your parameter. This denotes the joint observation, the joint distribution or the joint probability density function of the observation vector y bar and parameter h. Therefore, what I would like to do is to basically average. So, what now the mean squared error, the MSE, which we have represented as the expected value of h hat y bar, that is, let me just write this clearly, that is h hat of y bar minus h whole square. Now, this quantity can be written as, given the joint probability density function, I am going to integrate it, I am going to write this expression, and I am going to write this expression. So, this expression is basically h hat of y bar, that is the error. All right. So, this is the squared error. What is this? This is the squared error, that is h hat of y bar minus h whole square. I have to average this over the joint probability density function of, I have to average this over the joint probability density function of the parameter and the observation error. All right. So, this is an important expression. All right. So, let me take some time to explain it. So, h hat y bar minus h whole square is the squared error. All right, but it depends on a particular value of the parameter h and a particular value of the observation vector y bar. All right. So, now to get the average or this mean squared error, I have to average this random quantity, right, over the joint probability density function of both the observation vector y bar and the parameter h. All right, because as we have said, in the Bayesian framework, the observations y bar as well as the parameter h are random in nature. Therefore, to compute the mean squared error, I have to average this instantaneous quantity over the joint probability density function of the random of the observation vector y bar and the parameter h. Okay. So, that is what we are doing over here. This is your squared error. This is the squared error, which is a function of y bar and h. And what we are doing over here is averaging over the joint PDF of y bar comma h. And now I am going to use an important property of this joint probability density function to simplify this expression. Now we are going to use the following property of the joint probability density function, that is P of y bar comma h, sorry, this is not h bar, this is h, can be expressed as P of h given y bar times P of y bar. So, the joint probability density function P of y bar given h can be expressed as P of h the given y bar, the conditional probability density function of the parameter h given the observation vector y bar, times P of y bar, that is the marginal probability density function of the observation vector y bar. All right. So, this is an important quantity P of h given y bar. This is also the posterior probability density function. Or the a posteriori probability density function of h given your observation vector y bar. And what is this? This is the marginal probability density function of where PDF basically represents probability density function. This is the marginal probability density function of y bar. So, P h given y bar, this is an important quantity. This is the a posteriori probability density function of the parameter h, right. So, remember we said we have a prior probability density function of h, which gives information about the parameter h. Now, the a posteriori probability density function P of h given y bar basically gives the modified probability density function of h on observing the vector y bar, right. So, now we have the observation vector y bar. Having observed this vector y bar, what information does that convey about the parameter h? That is captured in this a posteriori probability density function P of h given y bar. All right. I am now going to use this, plug this simplification or plug this property of this probability, joint probability density function of y bar comma h in the expression for the mean squared error above and simplify the mean squared error as follows. All right. So, now I can write the same expression for the mean squared error. This is integral minus infinity, Remember there are two integrals, one with respect to y bar, the outer integral with respect to I bar, y bar, the inner integral with respect to h, and we have, well, h hat y bar minus h whole square times, instead of the joint probability density function, I am going to write it as P of h given y bar into P of y bar d of h d of y bar. Okay. And what is this? This is basically where we had your joint probability density function P of y bar comma h earlier. Okay. I am substituting for P of y bar comma h as P of h given y bar times P of y bar. And now I am going to simplify this as basically, first I am going to write the outer integral with respect to y bar, and I am going to write the inner integral now with respect to h. I am going to write it as follows, that is going to be h hat of y bar minus h whole square P of h given y bar times d of h, correct. Now, I am going to take all the quantities with respect to y bar, because P of y bar, this depends only on y bar. I can remove it from the integral, inner integral, which depends only on h. So, P of y bar depends this depends only on y bar. So, this is a probability density function of h given y bar. So, this depends only on y bar. So, I can move this into the outer integral, all right. So, this is basically your inner integral, correct, with respect to h. Let me just write that clearly. This is your inner integral with respect to h, okay, and it depends only on the parameter h with respect to your because in this inner integral with respect to h, basically y bar is fixed, because y bar is in the outer integral. So, we are carrying out the double integration in two steps. First, an inner integration with respect to h, you get a function of y bar, then integrate it with respect to y bar, all right. So, therefore, as far as the inner integral is concerned, y bar is a constant, okay. So, that is important to realize. For this inner integral, y bar is a constant for this inner integral, okay. Now, therefore, what I am going to do, all right. Now, let us take a look at this inner integral, okay. What is this inner integral? This inner integral is the mean squared error averaged over, what is this? This is the mean squared error, this is error or squared error average over the parameter h for a fixed y bar. That is for a given observation vector y bar. If you were to ask the question, what is the mean, what is the average of the squared error corresponding to a given observation vector y bar, that is given by this inner integral, because we are averaging only with respect to the parameter h while fixing y bar in the inner integral. So, the inner integral basically is the mean squared error average with respect to h, that is, it is a mean squared error for a fixed y bar, that is important. So, this inner integral is the MSE for a fixed observation vector y bar. That is the first important point to keep in mind, okay. Okay. Now, the second important point is basically that if we were to come up with an estimator h hat of y bar, remember h hat of y bar depends only on y bar, all right. So, if I obtain the minimum, obtain an estimator h hat of y bar, which yields the minimum squared error, or which will yield the minimum mean squared error for each y bar for a given y bar, all right. So, for a given y bar, if I obtain the minimum mean squared, if I obtain the estimator h hat of y bar, which yields the minimum error, I do that for every value of y bar, then naturally its mean squared error with respect to averaging over y bar is going to be, it's going to be the minimum mean squared error with respect to y bar, correct, all right. So, what I am going to do, I am going to now derive the estimator h hat of y bar, which yields, which minimizes the MSE all right. So, for every given y bar observation vector y bar, we derive the error, we derive the estimator h hat of y bar, which minimizes the squared error, or which minimizes the mean squared error averaged with respect to the parameter h. And therefore, now since this is the best estimator, or this is the best, or this yields the minimum error with respect to every y bar, naturally when you average the performance over y bar, it is going to yield the best performance. In that sense, it is going to be the minimum mean squared error estimate, all right. So, now how do we derive the estimate which yields the minimum error for a given y bar? So, to do that, Naturally, look at this, we have this expression for the mean squared error for a given y bar. All right, this is h hat y bar minus h whole square p of h given y bar d of h. This is the expression of the mean squared error for a given y bar. To find the best, to find the h hat y bar, that is the estimator which minimizes the mean squared error, we simply differentiate this with respect to h, differentiate with respect to h hat and set this equal to and set this equal to 0. All right. So, to find, so this is this mean squared error is a function of h hat. So, naturally to find the minimum, we differentiate it with respect to h hat and set this equal to 0. All right. So, now we differentiate this with respect to h hat. All right. H hat of y minus h whole square p of h given y bar d of h. Okay. Now, take the derivative inside, interchange the derivative and the integral. We have minus infinity to infinity dou by dou h hat of y bar. In fact, this has to be the observation vector y bar minus h whole square p of h given y bar d of h. Now, look at this, only this quantity here depends on h hat, this does not depend on h hat, okay, does not depend on this does not depend on h hat. Therefore, now if I differentiate this with respect to h hat, what am I going to have? It is integral, this is going to be integral minus infinity to infinity twice h hat y bar minus h, this is differentiating with respect to h hat, I have twice h hat y bar minus h p of h given y bar of times dh. Now, this has to be equated to 0 to find the minimum, to find the h hat which yields the minimum. Basically, I want to differentiate this and equal to 0, this we are equating to 0 basically to find the minimum. Okay. And now, what we get is basically what this implies is basically this implies, now this 2 cancels because we have 0. So, I can cancel the 2, this implies h hat of y bar p of h given y bar d of h equals integral minus infinity to infinity h p of h given y bar dh. Okay. Now, observe these two quantities, integral h hat y bar p of h given y bar d of h. Now, remember the important property of the estimator h hat of y bar. The estimator h hat of y bar does not depend on h. This integral is with respect to h. Therefore, since h hat of y bar does not depend on h, it can come outside of the integral. That is the important point. So, this does not depend on h, which means I can take this and move it out of the integral, which means h hat of y bar integral minus infinity to infinity p of h with respect to y bar d of h equals, this should be equal to integral minus infinity to infinity h p of h given y bar into d of h. Now, look at these two, this integral first, this integral is an integration of the probability density function p of h given y bar. This is the a posteriori probability density function of h. We are integrating this over the range minus infinity to infinity. So, when we integrate any probability density function over the range minus infinity to infinity, naturally the integral is going to be 1. Therefore, this integral is 1. Now, look at this, this is basically, what is this? This is the probability density function of PDF of h given y bar. I am multiplying this by h and integrating from minus infinity to infinity. So, this is basically the average. So, what is this? This is the expected value of h given y bar. All right. Remember, from the properties of the probability density function, if I take any random variable x, right, probability density function f x of x multiplied by x integrated from minus infinity to infinity, that is minus infinity to infinity x times f x of x dx, that yields the expected value of x. Here I have integral minus infinity to infinity h times the probability density function of h given y bar times dh integrated from minus infinity to infinity, that is nothing but the expected value of h, but for a given y bar, that is conditioned on the observation vector y bar. And therefore, naturally finally we have the estimator which minimizes the mean squared error is basically h hat y bar equals the conditional mean of h, and this is the most important principle of MMSE estimation, which basically says that, and that is it. This is basically the MMSE estimate of the parameter h for a given y bar. What is this? This is the estimate which minimizes the mean squared error. This is the MMSE estimate or basically the minimum mean squared error estimator, all right, and that is given by the expected value of the parameter, the average of the parameter, that is expected value of h given y bar, that is the conditional mean of the parameter h, that is expected value of h. What is this? This is your expected value of the parameter h expected value of the parameter h given y bar, and therefore, this simple and elegant result basically gives us the minimum mean squared error estimator. What it says is a very simple principle, that is basically the estimate which minimizes the mean squared error for a given y bar, for a given observation vector y bar, is basically the conditional mean, that is if you look at the a posteriori probability density function p of h given y bar, the probability density function of the parameter h given the observation vector y bar, and look at its mean, look at the expected value of this a posteriori probability density function, that itself gives me basically the best estimator, or basically the estimator which minimizes the mean squared error for a given value of h bar. Now, naturally, since it minimizes the mean squared error, which minimizes the squared error for a given y bar, it minimizes the mean squared error for every y bar, therefore, it minimizes the mean squared error on an average, that is when you average it over the probability density function of y bar, all right. And this is the most important principle of minimum mean squared error estimation, that is the h hat of y bar is basically the expected value of h, expected value of the parameter h given the observation vector y bar, all right, and that basically captures the essence of MMSE estimation. And we are going to use this principle of MMSE estimation further in wireless, in several wireless examples to illustrate the application of this principle of MMSE estimation, all right. So, we will stop this module here. Thank you very much.